So in this class we'll continue whatever we have taught in the last class. So that is relation lecture 3. Relation among gain margin, phase margin, and sensitivity function. And we saw sensitivity function means sensitivity peak, MS. In the last class, we saw that gain margin max, that means upper side gain margin, GM max is, we saw that GM max is greater than equal to MS by MS minus 1, and phase margin greater than equal to phase margin. We saw what is the relation of phase margin. Phase margin, we saw that phase margin greater than equal to 2 into sine inverse 1 by 2 ms. And these things we proved for a for a typical Nyquist plot, but it can be proved for any Nyquist plot in same way. That proof is valid for any Nyquist plot. Now the additional inequality is lower side gain margin, GM mean. So GM mean, you can prove that it is less than equal to MS divided by MS plus 1. So this you can also prove using a simple Nyquist diagram. For example, this is the Nyquist diagram. So one Nyquist diagram I am taking where both GM mean and GM max will be there. Such a loop transfer function we already considered in the last class. This is omega equal to 0, omega equal to infinity, omega equal to minus infinity, omega equal to 0 minus, this is 0 plus actually. So this is your minus 1 point. And this is a sensitivity circle. What is the radius of this circle? Radius of this circle, sensitivity circle is drawn such that it just touches this Nyquist plot like this. And what is this radius? This radius already we saw that this radius is MS inverse. And what is our lower gain margin? So this distance actually, this distance is what? 1 by GM max, and this distance is 1 by GM min. All these things we already saw in the last class. This is GM. So from the above figure, you can this inequality and this inequality we have already proved in the last class. So now this in GM mean, the inequality of GM mean I will prove. So from this figure, you can write that 1 by, sorry, I don't use this ink. From the above figure, one by GM mean. So 1 by GM mean is from here to here. 1 by GM mean plus 1. Sorry, 1 by GM is this distance. So 1 is this distance. 1 by GM mean minus 1. That means here to here. This distance is always greater than MS inverse. Greater than equal to MS inverse. So from here, from this one, this means 1 by GM mean is greater than equal to MS inverse plus 1. This means GM mean, that means lowest side gain margin, is less than equal to 1 by MS by MS plus 1. Okay. So the derivation is very simple. So for this figure, the derivation that I have done in the last class for GM max and phase margin also holds, and you can do exactly in the same way. So that means these relations GM max, phase margin, and GM mean with MS holds for any 9-piece plot. And also you can easily see that if you want to ensure, suppose GM mean less than 0.5, suppose you want GM mean, suppose you want GM mean is 0.5, so which is, that means minus 6 dB, that means gain margin in the loss side. That means loop gain, you can, the nominal loop gain you can reduce by a factor of 0.5. Then what is the MS limit? You must have MS by MS plus 1. This can be guaranteed. GM mean equal to 0.5 can be guaranteed if MS by MS plus 1 is less than equal to 0.5. Okay. So okay, GM means suppose less than equal to 0.5 I want. So this can be guaranteed if MS by MS plus 1 less than equal to 0.5. So this means MS less than equal to 0.5 MS plus 0.5. This means your 0.5 MS 0.5 MS is less than equal to 0.5 MS less than equal to 0.5. So this means MS less than equal to 1. So this is for a good design. Normally for a good design, as I said, MS is approximately equal to 2. MS is less than 2. So this implies MS is less than 2. So MS less than 2 means what? Your GM max GM mean is less than equal to 2 by 3. That means around 0.66 that you can guarantee. So now we will see robustness, how to take care of loop robustness against unmodeled dynamics. So far we have considered a sensitivity norm or sensitivity peak to tackle robustness against parameter variation. Actually, that sensitive peak is a good measure for robustness against parameter variations. But if you want to have some robustness measure against unmodeled dynamics, then what I have to do? That we'll see. So robustness against, if I want to derive some condition under which robustness against unmodeled dynamics can be guaranteed. So robustness against unmodeled or neglected dynamics. So suppose the actual plant, suppose the actual plant is G hat, so G hat is, so I will denote here actual plant is G hat and the approximated plan for which, or simplified plan for which the controller has to design as GS. Suppose G hat is suppose 10 divided by S plus 1 into S plus 10. So using dominant pole approximation, dominant pole concept, as you can approximate like this G hat is to 1 over S, because S minus 10 pole is far away from S equal to -1. So you can approximate G hat S to a first order system. The second order transfer function you can approximate to first order. So this kind of approximation is needed for controller design, because otherwise if you have a very higher order plant, if you do not reduce it to lower order, then otherwise controller order will become more and also controller design will become difficult. That's why for controller design, a simplified plant is obtained, and whenever you will obtain a simplified plant from a higher order plant, then some approximation you have to carry out like this, and some modeling error will be there. But controller has to be designed in such a way so that even if that modeling error is there, the controller will show desired output, desired responses even with the actual plant. So here, what is the modeling error? So before that, this is actual plant. So true approximated or simplified plant. Approximated or simplified plant. What is approximated or simplified plant? This GS equal to 1 over S plus 1 here. So this plant. So now what is the error? Modeling error. So modeling error. So modeling error you can obtain experimentally also. Suppose you have a true plant and you have approximated to it to some simplified transfer function. So you can obtain the approximate. You can obtain the modeling error in a lab also. Suppose your G hat is your true plant and G is your approximated plant, and what we will give? We will give a sinusoidal input of varying frequency omega, and you will see what is the error. So of course here I have assumed that both G and G hat are stable. So this is your EA. So G and G hat I have assumed here stable. So now, now what is error? EA. EA is what is the error? Suppose this is your GS, this is your G. From this figure, you can easily write the error as EA J omega mod EA J omega equal to what? This is frequency response. Sinusoidal input you are giving. So what is the mod value? It will be G hat of J omega minus G of J omega. So that means normalized error. EA divided by G of J omega. So normalized error, you can write like this. Normalized error will be G hat J omega divided by G of J omega minus 1. So this will become J omega divided by G of J omega. This will be equal to, if you put those values that we have, this values, this is GS G omega and G hat J omega. It will be like this. It will be minus J omega divided by J omega plus 10. So this will be equal to omega by root under omega square plus 1. So now if we plot it, how it will look like? Plot the normalized error. If we plot the normalized error, it will look like this. This is omega. This is the magnitude of normalized error. So this is suppose 1. So the plot will be like this. So here 3 dB cutoff frequency, 3 dB frequency will be 10 radian per second. 10 radian per second, and your this 3 dB frequency. So this is magnitude will be 1 by root 2, and you can see from this figure that normalized error increases with frequency. So at omega equal to 0, so this is 0, and as omega increases, it increases. So as omega small, that means normalized error is very small, and so normalized error is small at low frequency, and large. Large means here 1 is large because we have normalized it. Large at high frequency. So from this observation, what is the conclusion? Conclusion is this will imply neglected dynamics are dominant at high frequency. So neglected or unmodeled dynamics are dominant at high frequency. So your controller should be designed such that they should be attenuated, that their effect should be attenuated. This neglected dynamics should not affect the loop, particularly at high frequency. We have to take care of those things at high frequency. But at low frequency, their effect is very small because normalized error is very small. So now how to to guarantee the stability of a loop in presence of unmodeled dynamics. Before that, a general normalized error frequency response I will draw. So suppose the above frequency response I have shown for a particular example, but in general it will look like this. This is your omega. This is your magnitude. Magnitude means here magnitude of a normalized error. So it will look like this. This is your unmodeled dynamics, and unmodeled. So here WC. This is your WC. This is your WC J omega. So WC J omega is a high pass filter, and it has to be chosen such that your unmodeled dynamics normalized error due to unmodeled or neglected dynamics will always lie below this high pass filter WC. So this is your normalized error. So from this you can write that your normalized error EA j omega divided by G of j omega, normalized error equal to what? That is G hat j omega divided by G j omega minus 1. So this is equal to, right, you can write this is equal to delta of j omega into WC of j omega. You can see that delta E of j omega divided by G of j omega always less than equal to WC of j omega. And if you want to write like this, then what should be your delta j omega? Delta j omega should be less than equal to 1 for all frequency omega. Right. So now from this expression, how you can write the true plant expression, you can write like this: G hat of S equal to G of S into 1 plus WCS into delta S, where delta J omega is less than 1 for all omega. This is the true plant. So this is also known as multiplicative. This is also known as multiplicative parametric model. Multiplicative uncertainty model. Multiplicative uncertainty model. Because here you can see uncertainty. This is the uncertain portion. WCS into delta S. That is appearing as multiplication with GS. So that's why it is called multiplicative uncertainty model. Similarly, additive uncertainty model will also be there. So at that time, it will be G hat S is GS plus WCS into delta S. So, so that is additive uncertainty model. So in robust control course, all these things are taught. This is not there in our course, in this course. Now how to guarantee. So condition now condition for robust stability against against unmodeled or neglected dynamics. So what is the condition that I have to obtain? So I'll draw a diagram where one diagram is this is your actual plant G hat S, and this is your controller CS. So here deliberately I have not drawn any input output, as the stability will not depend on input output. In case of time invariant linear time event system, only loop is important for stability. That's why I have not shown any input output. So this is your true feedback system. True feedback system. And this is your approximated feedback system. G of S. This is your CS. This is the approximated feedback system. That means you have designed controller for this GS, not for GHS. But you have to obtain a condition for which this true feedback system will also be stable. So again and again I am repeating, controller CS is designed for GS, but that design should be such that if this controller is employed for the true system G hat S, then the true feedback system will remain stable. Now, so true loop transfer function or actual loop transfer function. What is your actual loop transfer function? L hat S from this diagram is G hat S into CS. So this you can write like this, L hat S. What is your G hat S? G hat S is GS into 1 plus WCS into delta S into CS. So this implies, this you can write L hat S equal to GC. GC means what? LS into 1 plus WCS into delta S. What is LS? LS is your nominal loop transfer function. That means loop transfer function corresponding to approximated feedback system. And that is GS into CS. So from here you can write L hat S. This is equal to LS plus delta S into LS into WCS. So now you can see the true loop transfer function is equal to approximated loop transfer function plus some perturbation. And this perturbation, maximum magnitude of this perturbation, what is the maximum magnitude of this perturbation? Since delta j omega is less than or equal to 1, so the maximum magnitude of this perturbation is mod of Lj omega into Wcj omega. So now I will try to draw the what will be the given a Nyquist plot of Lj omega. What will be the Nyquist plot of L hat j omega? Then I will obtain the condition for robust stability. This is your real of Lj omega or L hat j omega, Lj omega, and this is your Lj omega. This is imaginary of Lj omega. So suppose this is your nominal. Suppose this is your nominal loop transfer function, nominal Lj omega. So this is omega equal to 0. This is omega equal to infinity. 0 plus and infinity. And this is your minus 1 point. Minus 1 point. Minus 1 plus j0. So now this is your L j omega plot. Now what will be the L hat j omega plot? You can see L hat j omega is what? L hat j omega is L hat j omega equal to L j omega. L hat j omega is L j omega plus this perturbations. So you can draw, you can say at a frequency say omega 1. So L hat j omega will lie in the neighborhood of this point at a frequency say omega 1. So it will lie at the neighborhood of this point, but what is the region where within which this L hat j omega 1 will lie? So L hat j omega will 1 will lie within some, you can say within some disc. What is the radius of this disc? This radius of this disc is mod of L j omega 1 into W C j omega 1. Similarly, at omega 2, it will again lie within some disc L hat j omega 1, omega 2. But at that time, this disc radius will increase or decrease, because WC as frequency increases, WC magnitude increases. So at omega equal to omega 2, where omega 2 is greater than omega 1, this disc size will increase. Disc size will increase. Similarly, as the omega increases, disc size will increase. So like this, although I have not drawn this disc properly. So what is the radius of this disc? The radius of this disc at a particular omega is equal to, this radius is mod of L j omega into WC j omega. And the L j omega plot will lie within this envelope then. Okay. So now for robust stability, what is the condition? For robust stability, the L j omega Nyquist plot should not touch this Nyquist plot, this L j omega Nyquist plot. This is the boundary of L j omega Nyquist plot. L j omega Nyquist plot will lie inside this region. So L j omega Nyquist plot should not touch minus 1 point. So now, what is the distance from the nominal? So what is the distance from say the nominal Nyquist plot to the minus 1 point? The distance of the nominal Nyquist plot from the minus 1 point, say at omega, say at this omega. So this, what is this distance? This distance is 1 plus mod 1 plus L j omega. So that means this disc radius should be less than 1 plus L j omega. Then only this point will not touch this minus 1 point. So for robust stability, for robust stability, 1 plus L j omega should be more than what? Should be more than the radius of this disc. That means mod of L j omega into WC j omega. So this implies This implies your L j omega, WC j omega, okay. L j omega into WC j omega divided by 1 plus L j omega. This mod should be less than 1 for all frequency, for all omega, greater than or equal to 0. So this will imply what? What is L? So L j omega divided by 1 plus L j omega is, I will denote as T j omega. So WC j omega into T j omega is less than 1 for all omega greater than or equal to 0, where Ts, that means Ts is Ls by 1 plus Ls. So this is known as complementary sensitivity function. Complementary sensitivity function. So this also you can write, this is equal to, you can see it is equal to 1 minus s, where s is sensitive function. S is what? 1 divided by 1 plus L. So this implies s plus t from here, actually s plus t equal to 1. So for robust stability, against unmodeled dynamics, against neglected or unmodeled dynamics. So for robust stability and neglected dynamics, what one should have? One should have T of j omega into T of j omega should lie below this 1 by WC j omega for all omega. So this also one can also write, this is important relation. One can also write like that, that WC, that is max of omega, WC j omega into T of j omega less than 1. This implies, actually if this is for robust stability. So if this is guaranteed, you can guarantee this one, max of this one. So now that means what? For robust stability, against from this expression, what we are getting for robust stability? For robust stability against neglected dynamics, for robust stability against neglected dynamics, what one should have? Tj omega should be as less as possible. But the problem is Tj omega is Lj omega divided by 1 plus Lj omega. So it is not possible to make Tj omega small at low frequency. Tj omega is approximately 1 at low frequency, but the neglected dynamics becomes dominant at high frequency only. So only we have to make Tj omega small at high frequency. So Tj omega small at high frequency. So Tj omega small. So we should make Tj omega small at high frequency, this implies, so this is possible if Lj omega much less than 1 at high frequency. So that is all, that is clear from Tj omega transfer function. Ts is Ls by 1 plus Ls. So if Ls is small, then Ts will be small. So the objective the objective to tackle the way to tackle unmodeled dynamics is Tj omega should be made small at high frequency, and that can be done by making Lj omega small. So remember that Sj omega should be made small at low frequency, and Tj omega should be made small at high frequency. Sj omega should be made small at low frequency so as to tackle parameter uncertainty, and Tj omega should be made small at high frequency so as to tackle unmodeled dynamics. So because of this frequency separation, you can achieve this. Otherwise, this constant, this of course this s plus t equal to 1, this constant causes a lot of problem. Both you cannot reduce simultaneously. That is the water bed problem. So if you want to minimize TZW at a frequency, if you want to minimize the peak of Sj omega, so the peak of Tj omega will increase. So we have to trade off between the two. So Lj omega should be less at high frequency, as I said. So for a good design, mod Lj omega roll-up rate, mod Lj omega should have minus 40 dB per decade or more roll-off rate at high frequency. That means your typical plot of Lj omega will look like this. So at low frequency it is high, and then high frequency is low. So this is a magnitude, and at low frequency it should be high so that Sj omega will be less at low frequency. So this is the intermediate frequency. So why its shape is like that we will be discussing in the next class. Okay. Now we will consider a couple of examples to illustrate the method that we have discussed to tackle robustness against unmodeled dynamics. So example 1. So example 1 is consider. So in the example 1, suppose GS, your approximated plant is, well, G hat is, true plant is e to the power of minus tau s divided by s square. But when you are designing controller, your GS is, suppose you are designing neglecting this delay. So tau is delay. So suppose Suppose a PD controller. PD controller, I think you know all of you, KP plus KDS. PD controller is designed for GS to place the closed loop poles at S equal to -1, -2. Okay, so determine the amount of delay tau that can be tolerated. So remember that one thing I want to say, this whatever the robust stability condition this we have obtained, this is sufficient condition. This is not necessary. That means if this is satisfied, then you can guarantee the robustness against unmodeled dynamics. But if it is not satisfied, then you cannot. That means it is not like that. That if it is not satisfied, you cannot obtain robustness, but you cannot guarantee. To guarantee this has to be satisfied. So we will solve it. So you can write that you can obtain the error, normalized error expression as like this. Here the normalized error will become g hat by g minus 1 is what? Here e to the power of g hat j omega minus 1 e to the minus j into tau omega minus 1. So this you can write like that, this. So this is equal to cos tau omega minus j sine tau omega minus 1. So this you can write like this, root under cos tau omega minus 1 whole square plus sine square tau omega is tau. So this is equal to mod of 2 sine of tau omega by 2. Let's check it. So that means, so your normalized error plot is like this. Is omega. This is 2, suppose. So it is mod value. Mod is there, so that's why it is always positive. It will like this. Okay. So now we have to obtain a suitable high frequency weight WCS, so that that WCS will be tight enough. In that sense, it will be just the what is the minimum WCS, what is the WCS needed, so that this this normalized error plot will below WCS. Suppose this is my WCS. So this is my WCS. So WCS for to be in safe side, I am considering the peak is as 2.1. So this is your error. This is what your EA divided by G omega plot. EA G omega divided by error, normalized error. So for to be safe in safe side, I am assuming that the peak and the steady state value of WCS will be your this is your WCS. This is your WCS. So you can using a tight WCS using MATLAB, but for this example you can also obtain a tight WCS to some extent. Yes. So one can obtain so WCS when WCS will be high pass transfer functions. Let WCS will be like this, a high pass filter. We can consider like Ks by Ts plus 1. So if this is your high pass filter, then what is the steady state value of this WCS, WCG omega? Steady state S equal to 0, it is 0, and S equal to infinity, then W say infinity, this is equal to what? K by T. So K by T, so this implies K by T should be what? K by T should be equal to 2.1. This means K should be equal to 2.1 into T. Now, what is this slope? What is this slope? What is the slope of normalized error? Slope of normalized error from this expression, this will be 2 into tau by 2 into cos of tau omega by 2. That means the slope is maximum slope is tau. So what is this point then? This point will be 2 point. This slope is tau. So what is this frequency? This is suppose omega c. Oh, sorry, yeah, omega c. What is your omega c? So from figure omega c equal to, so here what is the slope? This slope is, so this slope is what? How much? Slope is tau. So what is omega c? Omega c will be 2.1. Omega c will be 2.1 by tau. Omega c will be 2.1 by, because 2.1 divided by omega c equal to tau. So omega c will be 2.1 divided by tau. So now what is the PD gains to place the closed loop poles at -1 and -2? To obtain PD gains. So to obtain PD gains now with the PD control, the closed loop pole polynomial becomes what? With the PD control, the closed loop pole polynomial becomes 1 plus GC equal to 0. So this means 1 plus G is what? 1 over S square, and C is what? Kp plus Kd into S. This is a PD control, Kp plus Kd into S. So this is equal to 0. All the PD controllers, PID control, all these things I will taught in detail later. But I think you know this one. Kp plus Kds is PD controller transfer function. So this will be equal to S square plus Kds plus Kp will be equal to 0. So on the other hand, what is your desired? On the other hand, what is your desired? The desired closed loop pole polynomial is what? What is the desired closed loop pole polynomial? S plus 1 into s plus 2 equal to 0. So this implies s square plus 3s plus 2 equal to 0. So this implies, so now if you compare 1 and 2, every coefficient of s to the 2, s to the 1 and s to the 0, then what will you get? Kd equal to 3 and Kp equal to 2. So comparing 1 and 2, so Kp equal to 2 and Kd equal to 3. So these gains we have obtained. So now we have to determine what is the condition under which this gain will ensure robustness against the delay. And what is the maximum? Oh, no, with this gain, I want to find what is the maximum tau that can be tolerated. So now, what is complementary sensitivity function? What is complementary sensitivity function? Then, what is your complementary sensitivity function? TS, complementary sensitivity function will be GC divided by 1 plus GC. So this is equal to what? Kp plus Kd into S, this is your C, and G is usual 1 over S square, and 1 plus GC is 1 plus Kp plus Kd into S into 1 over S square. So this will give you Kp plus Kd into S divided by S square plus KdS plus Kp. So this is equal to 2 plus 3s divided by s plus 1 into s plus 2. So here what was the problem? Suppose the PD controller is designed, determine the, okay. Suppose the PD controller gains, PD controller is designed, determine, okay, fine. Now we have to obtain, now we'll see what is the value of tau such that Tj omega plot, asymptotic Bode plot of Tj omega will always lie below 1 by Wcj omega. So asymptotic Bode plot I will use for this purpose. So this please check carefully. This is a very important thing. Omega. So this is radian per second. So I will use it log scale. Omega is log scale, and this is magnitude. Magnitude I will use normal scale, not dB, normal scale. So that means this is 1. This means 0 dB. So now if you draw Tj omega, so what are the cutoff frequency? Numerator 2 by 3, then 1, then 2. Although my drawing is not according to scale, this is 3. I have just extended. So I have just considered. So so for 2 by 3, so you can draw like this. Just check it. What is this magnitude? This magnitude is 1 by 3 by 2. That means 1 by 2 by 1 divided by 2 by 3. That means 1.5. 3 by 2. So this is 1.5 because this is in log scale, x-axis. This is 1.5. Okay, so this is your Tj omega plot, mod Tj omega. So now what is your WC? What is your WC? WCS is what? WCS is your TS plus 1 divided by KS. So TS plus 1 divided by k into s. So, and k equal to 2.1 into t. So the magnitude, so it's magnitude, maximum magnitude, that means at s tends to infinity. What is the magnitude? Magnitude is t by k. So that means approximately 0.5. Magnitude is approximately 0.5. So this is suppose this is 0.5, say. So how it will look like? So now what is the best? What is the minimum? Minimum means what is the, how you can draw WCS so that just it will be above TCJ omega. So at s equal to 0, as s tends to 0, magnitude is infinity, so slope is 1. So the plot of this one, will look like this. We can, so yeah, the plot of this one will look like this. So this is the plot of WCS. What is this frequency? This frequency will be 1 by t. This frequency is 1 by t. This frequency is 1 by t. So what is t? Okay, 1 by t. Or t equal to again 1 by omega c. So that means equal to 2.1. That is equal to 2.1 by omega c. Yes, 2.1 by omega c. T equal to what? Sorry, omega c is t equal to 1 by omega c. And what is your omega c? Omega c is again omega c. Omega c is 2.1 by tau. So here some error is there. Next to it. Okay, so this frequency is 1 by t. Now what is t? So t is, so what is your t? So t equal to 1 by omega c, that means tau by 2.1. T equal to 1 by omega c, that means equal to tau by 2.1. So t equal to 1 by omega c, that is tau by t equal to what? T equal to 1 by omega c, that is equal to tau by 2.1. Tau by 2.1. So that means 1 by t equal to 2.1 by tau. Okay. So now, so here slope is how much? Here slope is +1. Here slope is 0. This is 0. This is -1. So then as per this slope, if this point is 3, then what should be this point? This point is almost 0.5. So this is your, actually it should be 1 by 2.1. Okay, I have considered just 0.5. So this should be 6 radian per second. This should be 6 radian per second. 6. So then 2.1 by tau should be greater than, for robust stability. For robust stability, 2.1 by tau should be greater than 6. That means this implies what? Tau should be less than tau should be less than approximately, you can say, 3 seconds. No, yeah, it is 2 by 6. 2 by 6 means 0.3. 0.3 second. 2.1 by 6 3 sorry, 1 by 3. 1 by 3 means 0.31, say, or 0.31 second. So this is the answer. This is the tight possible bound. So more tight possible bound you may get using MATLAB, but as far as this figure is concerned, this is most tight. This is tight enough, because you just see here, this WC J omega is just above the TJ omega. So TJ omega will lie just below WC and J omega. So this is your J omega. This is your J omega. J omega. Okay. So another example we will consider. So example 2. Let G hat S equal to 1 by S minus 1 into 1 plus minus 0.2 S divided by S plus 10. So consider a proportional controller. Consider a proportional controller CS equal to K, designed for the approximated plant GS equal to 1 over S minus 1. Find the range of K such that the true closed loop system is stable. So here, so what is your WCS here? WCS is 0.2 S divided by S plus 10. So this means what? In time constant form it is 0.02 S divided by 0.1 S plus 1. What is your complementary sensitive function? Complementary sensitive function is GC by 1 plus GC. So this you can obtain as SK divided by S plus K minus 1. Just GS equal to 1 upon S minus 1 and CS equal to K. So if you put those values, then you will get this one. So now asymptotic board plot if you draw. So it will look like this. omega, this is radian per second, log scale. Remember that. So this is log scale. I should not write every time, but for the timing I'm writing. So this is a magnitude. So what is your W? What is your WC J omega? WC J omega will be like this. Your cutoff frequency is 10. So it will be like this. WC J omega plot will be like this. This is your WC. This is your WC. This is your WC J omega. WC J omega. So what is your Tj omega? Tj omega, suppose, so Tj omega should lie below WC omega, just below WC omega. Suppose your Tj omega is like this. So Tj omega will be like this. Slope is -1. Here also slope will be -1. And this value will be this cutoff frequency will be 1 by k minus 1, and this one will be magnitude will be k by k minus 1. Now your from this figure you can see that to guarantee, so this is your actually T, to guarantee that Tj omega plot will lie below WCJ omega, your 1 by to guarantee that Tj omega lies below WCJ omega, one must have what? 1 by k minus 1 should be less than 10, and also k by k minus 1 is less than, what is this value? This value is 5, less than 5. So if satisfying both the inequalities above, you can easily say, so from here you will get k less than k greater than 1.1, and from here you will get k greater than 1.25. So k should be, so overall, to satisfy both, so to satisfy both means this k greater than 1 as well as k this one, k should be greater than 1.25. So this is the, okay. So these two examples I have considered to show that how the robust stability condition that I have obtained for robustness against unmodal dynamics can be used for a given controller plant pair. So in this way, you can study robustness against unmodal dynamics after designing a controller. But this is not a synthesis process. This is a post-checking kind of process. Synthesis you can also do. So for that, you have to use H infinity and all those method. And H infinity controller design method that is taught in a robust control class. So these two examples I have considered. These two examples are interesting, particularly example 1. So the practical example, delay is normally not considered in the design. So, but delay is always inevitable. Delay will be always there in the loop because of computation or transportation lag. So the system, the controller should be designed such that even in presence of delay, uh, it should stabilize the system. I think everything is right. So if any error is there, then I will let you know in the next class. Any error means this minor error. Okay. Thank you very much.